All right, this is Precalculus, Chapter 4, Lesson 3, Graphs of Polynomial Functions. Do you remember what makes a polynomial function? What's the definition? Oh my goodness, Will can read. No variables in the denominator, no variables under a radical, okay? Which means they all have to have positive whole number exponents, all right? All right, so we're really focusing on this left-hand column, front and back, all right? All right. So what is the difference between an even and an odd function? So an even function means the degree is even, right? The degree is even. It's 2, 4, 6, 8, right? The end behavior we're going to talk about the end behavior. All right. The end behavior of the function, if it's even, is as x approaches negative infinity, y is going to approach positive infinity. And as x approaches positive infinity, y will approach positive infinity. So it doesn't matter. As x gets smaller and smaller, y gets bigger and bigger for every even degree function. And as long as you have a positive, this is positive lead coefficient. Positive lead coefficient, okay? And as x gets bigger and bigger, y gets bigger and bigger. Okay, so you can tell the end behavior. End behavior is just that. As x approaches negative infinity, what happens to y? And as x approaches positive infinity, what happens to y? That's what happens at the very end of this curve is what it's asking. That's what end behavior is.
What does the LC stand for again?
Lead coefficient. Positive lead coefficient. Yes.
Could y ever even out so it's just x approaches
Yes.
infinity and y is 4 or something?
Approaches a number. That is correct. But that's with asymptotes. We're not going to deal with that yet. But yes,
Wait,
yes.
we're back to asymptotes again? Exactly.
We're going to get there. Not today. Yes.
Okay, so basically when
There are no asymptotes with polynomial functions. No asymptotes. Only with rational. Okay.
okay, so when it's even, it's the same. When it's odd, it's different. And with the positive leading coefficient, that means the first one is
Positive.
the first one. Is
Yeah. So this is positive 4x to the fourth. Yes.
And if it was negative, that means the first.
Correct.
Okay.
Okay. If the lead coefficient is negative 4x to the fourth, then it's going to look like this. Just like our parabola. If that lead coefficient was positive, it opened up. If that lead coefficient was negative, it opened down. But now I'm using different language, right? So if that lead coefficient is negative, then as x approaches negative infinity, what does y approach? Negative infinity. Okay, I'm using calculus language here. All right? And as x approaches positive infinity, what's y approaching? Negative infinity. So notice with our even degrees, it doesn't matter what x is approaching positive or negative infinity. Y is always approaching the same value, positive infinity or negative infinity. Got it? with every even degree. If we have an odd degree, that means we have like an x cubed, an x fifth to the fifth, x to the seventh, any odd degree function, the end behavior is just going to be the opposite. All right. If we have a positive lead coefficient, it's going to go start in quadrant 3 and end in quadrant 1. So, as x approaches negative infinity, what does y do? Negative infinity. As x approaches negative infinity, y is approaching negative infinity. And as x approaches positive infinity, y is approaching positive infinity. Now, if we have a negative lead coefficient, we're going to go from quadrant 2 to 4. We're going to start in quadrant 2, the squiggles in the middle, and end in quadrant 4. So when I have an odd function, odd degree function, with a negative lead coefficient, as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y is going to approach negative infinity. Yes, ma'am.
So will they always go at like a diagonal away from the origin, or will they ever like swing back?
If they swing back, it's not a polynomial function. Because by definition, every x can only have one and only one y.
Yeah.
Got it? So it can't swing back. So it's not a function.
Is
All
there
right.
some point where there's some hypothetical realm of mathematics?
No, because
If it's not a function, it can. Yes. Okay?
Did you see the new
All right.
square?
So, can you what?
Did you see the new square that they made?
No. But let's keep going.
Okay.
All right, ask me about that in a little bit later. All right, so this is true with all polynomials. When we look at the degrees, you should be able to visually know, does it open up, does it open down, does it start in quadrant 3, end in quadrant 1, does it start in quadrant 2, end in quadrant 4? So visually you should be able to know, right? The degree of the function also tells us at most how many x-intercepts. So if I have a 5th degree function, how many at most x-intercepts can I have? 5, right? But I can have less than 5. All right? Now, what else is a property of a polynomial function? Look on the bottom of page 261. And I am going to differ with your textbook here. All right. This is called continuity. I know you have heard this as continuity, right? But in math, it's pronounced continuity. All right. Students really don't like me saying it that way, but I'm telling you, I've watched enough math videos.
It sounds right.
It's continuity.
Yeah.
Okay. All right. Good. Excellent. Okay.
I have no issue with that.
Thank you. Okay, there we go. Here we go. We're going to talk about continuity and discontinuity. Got it? All right. So every graph of a polynomial function is continuous. This is what continuous means. It's an unbroken curve. That means if I start, I don't ever have to lift my marker off the board to finish the curve. All right, so it is an unbroken curve. There are no jumps, there are no gaps, there are no holes. Your book says it cannot have sharp corners, I disagree. A polynomial function can have sharp corners. All right? So when you're answering your homework, just take that in note. So look on the top of page 262.
What's the difference between a jump and a gap?
A gap is where an asymptote is.
Dang it.
Yeah.
Not the asymptotes again.
Okay, so a jump would be like, I go here. A jump would be like a piecewise function. I say below x is -2, I go here, and then above it, I go there. So this would be a jump. That is a hole in the graph. Those are points of discontinuity.
So a gap is symmetrical.
A gap, yeah, would look, a gap, I'm just going to draw one like it is. Okay, I'm going to draw one like this. So so there would be this gap in the middle. Or a gap could look like that, where there's this vertical line that can be drawn between them. And I disagree with the sharp corner.
So they're mirrored in some way. Gaps are.
That tells me, really, a gap tells me it's a rational function. It's a polynomial divided by a polynomial, which we're going to get to.
I hated those.
Okay, we're going to get to that. All right. Now, I've already discussed end behavior, but look at the bottom of page 263. Look at those images. The first one is 2x to the 4th. What's the degree of that function? 4. What's the end behavior going to be? As x approaches -infinity, y is going to approach positive infinity. And as x approaches positive infinity, y is going to approach positive infinity. Same with 2x to the 4th. Now look at the bottom. -3x to the 6th, that's an even degree. It's a negative lead coefficient.
But it's negative.
So it's negative as x approaches -infinity, y is approaching -infinity. As x approaches positive infinity, y is approaching negative infinity. You got it? I already taught that. And you can look on the top of page 263. There's our odd functions.
Wait,
If
so-
you just saw top of page 264, I do think I said 263. Look, positive lead coefficient goes from quadrant 3 to quadrant 1. Negative goes from 2 to 4. Make sense? Okay. Now let's talk about the intercept. So you've got end behavior, right? You understand end behavior?
Mm-hmm.
Yes.
To refresh.
This.
Oh, yes.
Okay.
So
If there's a jump in the graph, if there's a hole in the graph, if there's a gap, it's not a polynomial function. Got it? Now, intercepts. How many y-intercepts does a polynomial have? Only one. If it has more than one, it's not a polynomial.
Right,
Because it's not a function. There's got to be something in, y has got to be squared. All right? All right, so every polynomial function has one and only one y-intercept. And when a polynomial intercepts the y-axis, the value of x is 0. So, what's the y-intercept? 6. Got it? All right. How many x-intercepts can this have?
4.
Can have 4. Can it have 3?
Yes.
Can it have 2?
Yes.
Yeah.
It can have between 4 and 0.
It's 4 because of the exponent, right?
Correct. So it can have 4. It can have 3. It can have 2. Or it can have 1.
Or 0.
Or it can have 0. I'll draw this one down here.
And that would be imaginary.
4 imaginary solutions, yes.
Ew.
Lovely.
Okay?
Yep.
All right. We talked about multiplicity. Multiplicity of a factor tells us if the factor intercepts the x-axis or touches it and returns. And multiplicity is the exponent of that factor. All right, so say that's at 1, and we'll say that's at 3. All right. When it crosses, this is all, okay, this is on the back. Multiplicity is on the back of your sheet. It tells you how many times a particular number is a 0. It's the exponent. Got it? If the exponent is odd, it crosses. So this could be x minus 1 cubed, as long as that exponent is 3. So this one has a multiplicity of 3. So 1, 3, 5, 7, 9. Any exponent of a factor that is odd tells you that it crosses the x-axis. Got it? For this one, because it doesn't cross the x-axis, then the multiplicity of the function has to be even. So this could be to the 4th power. That factor could be to the 4th power. Any even number.
But could it be 2?
It can be 2. It can be 2, 4, 6, 8, 10, 12. Any even number. Got it? All right. So look at example 1. All right. And they have this. All right. What is the degree of this function?
6.
The degree is 6. So what do we know about the end behavior?
It's going to be like
Open up, right? Because there's a positive. So it's going to open up. It's going to start in quadrant 2, end in quadrant 1. All right. What are the zeros?
-1, +2, positive.
Let's pick.
-1, 2, and 3. All right. What is the multiplicity of this 0? -1.
Even.
It's 2. So does it cross or touch?
Touch.
It only touches. Touch or cross, intercept, okay? What's the multiplicity of 2?
1.
1. So does it touch or cross?
Cross.
Cross. What's the multiplicity of 3?
3.
So does it touch or cross?
Cross.
Crosses.
Okay, could I? Got it?
Wait, there was-
Yes.
There was, wait.
What is the Z in the end?
0 multiplicity. See?
Where do you get the multiplicity from? Like, I know that.
Right here. That's the multiplicity.
If the exponent of a factor is specifically the factor, then it means that at that 0, it can either touch or cross.
If it's like expanded, should we add them?
And zeros are the opposite of the.
You mean it's already multiplied out?
Well, like, if let's just say it said x plus 1, x minus 2, x minus 3, x plus 1. Would we add the x plus 1s to get the multiplicity?
Yes.
And the 0 would be,
The opposites.
yes.
Okay, can I know the y-intercept?
Yeah.
Probably.
Yeah.
Okay, help me figure out what the y-intercept is.
Is it 7?
Well, it's going to be 1 squared times negative 2 to the first power times negative 3 cubed. It's going to be the last ones multiplied.
Wow.
Okay?
Fancy.
What is that? That's negative 2 times negative, is that 27? So positive 54,
And what is that?
the y-intercept. I have a lot of information here. I could actually sketch a rough graph of this. I have all the x-intercepts. I know if it crosses and touches. We're going to say this is 54. That's my y-intercept. We know at negative 1, it only touches. We know at positive 2, it crosses. And at 3, it crosses. And we know where it starts.
Quadrant 2.
We know it comes here. We know, did we say it only touches at negative 1?
Yeah.
So it touches, goes back up to 54, crosses, comes back up.
But I thought it would have 6 humps, or 5 humps.
It does not necessarily have 5 humps. Well, there could be a wiggle in here,
Okay.
right?
There is one on the.
Because it's
There
6
could be,
degrees.
but so this is called a rough, right? That would mean there's a couple imaginary solutions. All right,
Had to sneak that in.
all right. That's only example 1. Okay, everybody look. Now we're going to talk about, look on page 266. So I'm going to really go fast through here. Local extrema. That's your maxes and your mins. This also is on the back of the sheet. The degree of the function helps us to know how many local maximum and mins we potentially have at most. So this is at most, just like our x-intercepts, all right? At most, we have the degree of the function minus 1 maxes and mins. So if I have an x squared, you know there's only 1 max or 1 min. If I have an x cubed, I have at most 2 extremas. I have a max and a min. If I have an x to the 4th, how many do I have? 3. Got it? All right. So those are maxes and mins. Points of inflection is the degree minus 2, because does a second degree equation have any points of inflection? No. It's only either concave up or concave down. Points of inflection is where concavity changes. Points of inflection is that midpoint between a max and a min. So if I have something like this, that's a max, that's a min. The midpoint would be a point of inflection. So it's concave down from negative infinity to the point of inflection. And from the point of inflection to positive infinity, it's concave up. Got it? All right, so example 2 just asks, can we see a complete graph? So it's x to the 4th. You're looking for the end behavior. You're looking for it to open up, starting quadrant 2, ending quadrant 1, right? And that will tell you if your window is right. If I see an x to the fourth, if I'm graphing an x to the fourth degree equation, and all I see is it in quadrant 3 and ending in quadrant 1, my brain should say, I need to go smaller on my x. Make sense? If I have an x to the fourth and I graph it, and that's all I see, that does not look like a positive lead coefficient x to the fourth. I'm missing something over here. So now you should be able to know that. Do I see the complete graph? Make sense? That's what examples 2 and 3 are. And 4. Do I see the complete graph? Got it? So let's just look at 4. It's an x to the fifth. The lead coefficient is positive. What quadrant should it begin in?
It should begin in 2 or 4. 2.
It's
Yeah,
gonna
two.
start-
It's an x to the fifth. Positive lead coefficient. Example 4.
Third.
The third quadrant. It should begin down here. Right?
But it's
Oh,
positive.
yeah. Yeah, but it's
That's correct, but it's an odd degree. Odds begin 3, end in 1 if that lead coefficient is positive.
When did they talk about that?
The very first thing I said, end behavior. End behavior. All right? So look at those. There are 2 sets of 4 graphs early on. All right? My x-intercept is going to be 4. So if at the bottom, if I graphed it, everybody look at me, and I see this, and it's an x to the fifth, your brain should say, no, what does that look like? An x to the fourth with a positive lead coefficient, right? This cannot be it. I need to go more negative on the x-axis. And when you go more negative on the x-axis, this is what you see. This looks right. It begins in quadrant 3, ends in quadrant 1. So you're going to be able to know. Huh?
10 million.
What?
Oh yeah, 10 million.
What?
5 million. Tomorrow.
Actually, it just goes from negative 115 to 50. That's got to be on the y. That's crazy that they would go on the y-axis. I don't care if I see the humps, right? Those are the maxes and mins, unless I'm solving for the maxes and mins.
It's like-
Then I need to see the curves. All right, so this lesson is all about, can I recognize, is my window showing me all the x-intercepts that I need? So, it's all been about rational zeros. Rational and irrational. All been about real zeros, not imaginary. Make sense? Okay, so you know the degree of the function tells us the end behavior. The lead coefficient changes the end behavior. Multiplicity. You know multiplicity now, right? You know your x-intercepts. You know your y-intercept, right? And you know whether or not at those zeros does the graph cross or touch the x-axis and return. Makes sense? You know at most how many maxes and mins we're going to have. The degree of the function minus 1. You know how many points of inflection you're going to have. It's the degree of the function minus 2, because a second degree function has no points of inflection. It is either all concave up or all concave down. All right?